Hello, we are the Rite Solution ML research team. Our technical directors consist of the CTO of Rite Solutions, Thomas Santos, and its software engineer of Rite Solutions, Dana Brown. Our team consists of two electrical engineers, James Morris and Andrew Gomes, and a computer engineer, myself, Anthony Neves. Rite Solutions is a veteran-owned small business established in Middletown, Rhode Island. Founded in April 2000, they are best known for their warfare and business systems development and sustainment, including systems engineering, software development, information technology, and cyber engineering. The motivation of this project is to design software that utilizes machine learning and sonar detection to distinguish objects found underwater. This can lead to deeper and safer underwater explorations.
To achieve our anticipated best outcome, we need to be able to test our software with simulated data, which we're going to use MATLAB to do. We also need to translate the existing Python code into Rust, which is a more safety-oriented language, which is particularly useful when we're using an unmanned underwater vehicle. And we need the translation to be able to be applicable for future Rite Solutions products that may involve this software package. If we do all these, then we will achieve our anticipated best outcome of designing a software package that can quickly and accurately detect objects underwater. There is an existing machine learning model for detecting objects underwater that is in Python. In order to compare data between Python and Rust, we need a simulation environment in MATLAB that represents a sonar, so we can test between both the Python and the Rust models of the machine learning algorithm. So far, we have that sonar simulation in MATLAB for simple conditions, and we also have received energy feedback from that MATLAB environment. We've also begun to translate the existing Python code into Rust in order to compare the results. Our anticipated best outcome is a software package. That software package could be utilized in the commercial industry, where it could be used on a product similar to a fish finder, or it could be used in the military to try to discover landmines or enemy vessels or different shipwrecks, or it could be used in the research sector where it's used to discover wildlife, such as animals and plants that we haven't yet discovered. So the economic impact is largely dependent on how this software is implemented. I'm now going to talk about the simulated data that we are going to use to test both the Python and Rust models of our machine learning algorithm that we generate through MATLAB. I've been working in MATLAB to develop a sonar simulation environment. We started off with an example code from MapWorks that also simulated an active sonar system. The targets of that code were points in the ocean that had designated target strengths. I changed those targets to be 3D objects that created target strength patterns based on the shape of those objects. I then created my own sonar simulation with hydrophone projectors, transmitters, and receivers to emulate a towed array sonar. That towed array projection can be seen on the right. These two plots are to compare and contrast the output of the active sonar example when using a point versus using a 3D object. On the right is the original code where there is a point in space with a designated target strength, and on the left is after I replaced that with a cylinder. So as you can see, the pattern is relatively the same, however the amplitude for the object is much greater than that of the point. This is important because this means that the actual shape of the object is affecting the strength of the received signal on the sonar. Here's some basic information about my sonar simulation code designed in MATLAB. It's designed to be a towed array sonar simulation, meaning it's below the surface level of the ocean. It has extra plots with additional information compared to the previous code, which we just discussed, and it's all heavily commented, user-defined, and easily followed along for future editing, whether it be by us, by Rite Solutions, or by a different group of students looking at our work. And all parameters are defined to be easily altered to represent different sea conditions. Here are 3 plots that are outputted from running that code, and on the right you can see the paths between the source and the 2 targets. In the middle is the plot of the 2 targets themselves, and on the left is the received data at the sonar. And on the next slide, we're going to see all of these change with different parameters. On the right, we can see that the sources and targets are in different locations. We can see that the targets themselves in the middle plot are of different sizes and locations. And on the left, we notice a different pattern in integrated received pulse data, and we notice that the amplitude of the maximum is lower. These 5 plots are the result of running the simulation once, and in the bottom right is the only new plot here. And this shows the bellhop paths between the source and the receiver based on the water conditions, which is going to be more influential as we move forward and try to make this code more complicated in terms of parameters that affect the output. My short-term goal is to improve the sonar simulation code. I'm going to start by changing the towed array projection to a side-scan sonar projection, which means raising the source to sea level rather than beneath the surface of the ocean. Then I'm going to add the 3D plot of the object as well for reference. And then I'm going to clean the code of any unnecessary variables or definitions and make sure that the code is as easy to follow along as possible for anybody who opens it. Then I'm going to output integrated pulse data, which was a plot that we saw where the sonar receives the amplitude of the signal back across time. And I'm going to output that in comma-separated value format to test the machine learning algorithm. Then I'm going to add in a function that saves parameters that affect the integrated pulse data along with the integrated pulse data itself for reference. The current sonar simulation model takes an object's surface and creates a target strength signature object based upon that surface and the associated variable target strength with that object. Then energy is transmitted to the target strength signature object and feedback is received by the sonar. We need to eliminate the creation of a target strength signature object and the need for target strength in general, because we cannot arbitrarily assign target strength to objects in the real world. To do this, I'm going to create a sonar emission and detection program as opposed to a transmitter and receiver. The transmitter and receiver models have strict definitions in MATLAB and do not operate easily without target strength. Sonar emissions and sonar detections operate based on sensors, and you can manipulate the signals more freely. Therefore, it should be easier to assess the surface of an object from the point of view of a sonar using the emission and detection instead of transmitter and receiver. And we will compare these differences and make sure that we are more accurate in object detection, with whatever model we move forward with. Next, Anthony is going to discuss the computer engineering side of the project.
The ML model of the program in Rust takes in simulated data points from the aforementioned MATLAB code, finds which points of data are the closest together, and uses this to find an average overall shape for the detected object. In order to accomplish this, the programming language Rust must be learned, and subsequently, the provided code must be translated from Python and TensorFlow into the Rust language. When looking closer at the individual components of the program, we see that there are many parts working together. The dataset component is the individual data points provided by the MATLAB code. This component holds the three-dimensional position of the detected point. The distance component aids in holding the relative distance between two datasets. When looking towards the cluster component, we see that each cluster holds information about each point that is close to each other within that cluster. It holds this information by acting as a binary tree for the data. By clustering the data in this way, we can get a better sense of what the overall shape of the object looks like. We do this with the use of the manifold component. This component looks at multiple clusters from the dataset and finds any overlapping volumes between them. This is done with the help of the graph component and will tell us what the actual object should look like. In order to ensure we are getting the right output, the Chowda component, or the Clustered Hierarchical Anomaly and Outlier Detection Algorithms component, is used to detect anomalies from the provided data. At this time, I am completing my research on the use of the Rust language, and am confident that this information will help moving forward in the translation of the provided code. The provided Python and TensorFlow code is currently being translated, and this translation will continue into the long term between myself and our technical director, Najib, in order to achieve the anticipated best outcome. Once all the code has been translated, we will begin to test the program with predetermined parameters in order to ensure functionality. Once this is ensured, we will begin tests utilizing simulated MATLAB data to see how the program does in real-world scenarios. If there is time remaining, after this testing phase, we will begin the design and implementation of a user interface for the program. This UI will enable a user to see a 3D visualization of the results calculated by the program. Next, Andrew is going to discuss this 3D object visualization.
One of the first tasks given to us by our team and ourselves was to generate 3D shapes in an isobathymetry plane. During our tenure at URI, we have done tasks similar to this in our respective courses. As shown in the figure, this task proved to be successful as multiple shapes, including spheres, cylinders, a pyramid, and the MATLAB logo, were generated. This in part connected to the tasks of assistance to the Sonar attempt code and the simulation of various tests of said code. To help outline how we would achieve our anticipated best outcome, we crafted a high-level design document detailing the proposed steps towards our goal. All of the steps were to be done in MATLAB before running a real-life example. It would begin by selecting a commonly found undersea object, such as a shipwreck, landmine, pipeline, shipping container, or etc., which would then be represented through developed 3D shapes, applicable for machine learning purposes. That object would be placed on the isobathymetry plane, where depending on if the object is deemed correct, meant either the necessary adjustments would need to be taken, or we would proceed and apply energy to the received feedback. Once the data is received back from the object, that data can be represented in a desired output format. This step can also lead to the integration of more factors for the reception of feedback, including noise, water temperature, water salinity, and such. Here are some more examples of the graphs from the Sonar attempt code that James had showcased earlier, when given different parameter values. The image on the left displays the detection of objects a certain distance away from the given source, while the right image displays the generation of acoustic paths for spatially varying sound speed profiles in the bellhop ray tracing program. Here's another example of the integrated received pulses from a different attempt at running the Sonar attempt code. In the image on the right, the transmitted pulses appear as peaks. The two direct paths of this channel have the highest amplitudes of the graph, with the second pulse having the higher of the two, indicating a shorter propagation distance. The delay times for the paths can be explained as they are propagating through slower paths of the channel. To get to our anticipated best outcome, the main key technical accomplishments that must transpire are determining whether side-scan sonar, which has been our main focus, can best represent energy that is displaced in water, as well as using real-life examples as stated earlier in the high-level design document to gain the best and most accurate data. As a team, we are striving towards these future goals of 1. Continuous translation between Python/TensorFlow into Rust to be used according to Dr. Daniel's research. 2. The design and implementation of user interface for accessibility and ease of use. 3. Adding environmental factors into sonar simulation, such as the water temperature, salinity as stated earlier, as well as signal noise. 4. Generating sonar emission and the detection model using target strength objects. And 5, similar to task 3, we would like to gather accurate testing data for object detection under different ocean conditions. Lastly, we would like to thank and acknowledge everyone displayed here for their participation and guidance throughout this project.